So let me just set the stage up front. Removing actually the author of the book says removing a node from a binary search tree is one of the most complicated algorithms that they talk about in the book. Um, it's not it's not actually bad to code if you have some sort of spec in front of you. If you have to see the algorithm, putting it together and writing it down, it's not the worst. It's not super intricate as long as you're accurate in typing in code. But conceptually, it's really hard to see what's going on. It's hard to understand the rationale of what's going on. So that's what we want to talk about a little bit in this video. So we'll talk about how you play with it from there, but let's kind of scan through different ways to remove. There's actually two ways to remove. Just to be fair, for simple tables, it doesn't work quite as well with sets, though I have a theory that we might play with in class on how to make this happen. But for simple tables, when I have a key and a value, there's an option to do a lazy way of removing that just simply says if somebody says remove something that has a key, just set that value to be null. You don't actually have to delete it from there. It's kind of like instead of ripping a page out of the book to say remove it, just simply whiting out over the whole page. It's still there, it's just blank. We'll talk about that here in a second, but that's one strategy. The other way is the actual tough algorithm, which is how do I go through and get that node out of the tree but keep it balanced at the same time. So the lazy removal technique is valid. It means that all we have to do is use the contains, the find. Essentially, we do an add, but we do an add where we set it to be null at that point. We just change the value. We know it's already going to be out there in theory. Um, the one caveat inside of here is you have to make it so you do not need to store empty values, null values, to be in a coding sense, inside of your symbol table, inside of your map or your dictionary. If you need to store empty values for some logical reason, then this doesn't actually work as a reasonable way to do that. But it's not rare, it's not common that you need to store empty values. I mean, normally just not being in the dictionary, in the map, in the symbol table is a good enough state of for most applications working with it. So the great part about this algorithm is it's really great because you can either do an asynchronous removal of things from the tree. So essentially, you don't have to worry about deleting nodes and balancing nodes in real time. You don't have to slow down the whoever the caller is by removing nodes at that point. You think of it this way: you have a whole team of people who work in the office all day. They don't often clean up after themselves at the end of the day. There's people who come in overnight who, I mean, within reason, clean up after themselves, but they'll sweep the floors, wipe down surfaces, all that sort of stuff. The cleaning staff, essentially, that's essentially the same model as we're talking about here. Or simply, I don't care about ever deleting the nodes. I have enough memory that I don't really care about that. Maybe the server or the computer, or whatever, restarts every day anyway, and so there's no reason to delete them because the next time I start up, they just won't be there. It'll only load up the ones it needs. That the deleted ones just can essentially go away. So there are situations where being lazy in your code and not taking something away isn't necessarily a problem. That heap memory space might not. It doesn't really matter anyway if you have plenty of it. So probably would go without saying, but eager deleting is certainly more involved. It is something that is very intricate. I'm going to give you the best overview I can. I'm not going to say that I'm an expert on this. There might be gaps in what I say here. I'm going to give you a high level view of the way I understand the algorithm and the way I read it from going to code. And I'm not trying to really kind of backtrack inside of there, but there might be other implementations of this you might run across as well that might change the accuracy of some of what we go across. And just know that's always the case. There's always nuances and tweaks to algorithms. So the first thing we can do to make our lives a little bit easier is we need to make sure before we start removing that the thing we want to remove is actually even in this set. So this is kind of violating a little bit of some common sense at some level. So if I say I want you to remove this book from the library, you don't first run over to the shelf and say, does this library even have this book? And then go back to the person who said, yes, we have this book. Would you like to remove it? And then walk all the way back to the library and go remove the book again. That doesn't make sense from an effort standpoint. But in this case, it actually does, because trees, to see if it's in a tree, is a log n order operation. And if we know that the value is in the tree, we can actually optimize the removal process by starting to clean up the tree as we go and search for the item in question, instead of having to do it entirely after the items are removed and have the balancing process go on its way down as well. We can actually start to reorder and rebalance the tree as we move down the organization. So that makes this algorithm even more efficient than it could be otherwise, but also even more complex than it would be otherwise. So the first step before we even get into the recursive aspects of recursion is making sure the root is ready to go. We want to check if both of the root, if both the children of the root are red, are black, excuse me, then mark the root as being red. Because remember, that root might change positions. The root of a tree is always black in a stable state. But knowing that that root might change, might be rotated left or right, we're going to mark it red as being saying, hey, we, if this gets moved, we want to go and balance the tree accordingly. And so after we prep the the tree by marking the root as red, then we're going to actually make the recursive call to go remove the node. And then once we get back from that recursive call, whatever the node ends up being, we want to take that node back to black. The root should always be a black node inside of our logic. So that's a little bit of some tiny little prep before we even get into the recursive call. So let's talk about the high level outline of what that recursive call does. So by the way, this algorithm is not in the book. The authors of the book, saying it's one of the most complicated algorithms they do, they say as well, like, hey, why don't you go ahead and leave this example as being something you code on your own. It's a very happy thought. Like, let's take the hardest thing you're going to see and make you do it by yourself. It's a high expectation move by the authors, but the reality is, we'll talk about it in a second, you can get the algorithm in other places. So don't, again, try and reverse engineer this logic unless you really, really want to take on a challenge. All right, so the high level outline then of this recursive remove function is it starts by saying if the value is less than the root of the subtree, again, it's recursive. So it might be the actual root, it might be whatever tree, whatever navigation down the tree it is, whatever subtree that is. So if it's left of if it's left of that, we're going to go one path. If it's greater than or equal to, we're going to go the other path. And then after we pick out which path we're going to go to, we're going to make whatever recursive calls down the tree. We're going to balance it afterwards. So basically the remove function modifies the tree on the way down, and then it cleans it up and balances on the way back up. And so the balance should be less cumbersome because I modified it on the way down. But we still need to make sure we clean up how we're tweaking the tree as we go find the node to remove. All right, so let's talk about the left-leaning side. So the smaller than the subtree roots value. So if the left child and its left child are both black, so we know we have two nodes that are not in between nodes here. We have a nice standard 1-2 tree structure, binary tree structure. Then we want to actually choose to move that subtree left. So there's this function that is only used in remove called move left and move right. They're very similar to each other. So if we have the situation where we have only binary nodes, we want to make those nodes into 2-3 nodes essentially, and that's what this move left does. And so the first thing we do on that root is we flip the colors. So they were both black, so now they're both red, and then whatever happened to this, if it was red, now it goes to black. All right, and so if at that point the right child's left child is red, only if this is the situation, not if it's otherwise. But if the right child's left child's red, as we see here, then we're going to go ahead and rotate that right. So then at that point, we're going to take the whole structure from the top and rotate left with that again. So we went to the subtree on the right, rotated right, then we rotate the top structure left. Now notice we are essentially adding one node to the left. We know the node to be removed is coming from the left, and so we're basically making space for that to go away on the left. That's what kind of these steps are setting it up to be. And so when I delete it, it's going to be less likely I have to do massive structuring on the tree on the way back up because I've already balanced it before I've even got there. All right, so then after I've done those couple steps, I go recursively call remove on the left child. So where I was working on this node before, I moved up to here and moved this right stuff up, and then I go do the same thing on this left child. And so the exact same algorithm. It might do all those steps, it might do some of those steps, it might do none of those steps, depending on where everything is panning out. All right, so now the same pattern falls for the right value, right or the same. And so I'm not going to go through and talk about each and every, I don't have an animation to show you each and every one of those little manipulations that goes here, but it's just what we saw before. So if the left child is red, as you can see up here, so we're talking about the node at the top, if the left child's red, we're going to rotate that right. And so, that the process of rotating right, we already saw it up above. This left child becomes the parent becomes the right of the left, and so on and so forth. So again, the strategy is, I know that the thing's going to be removed from the right. I want to go ahead and find some, give it some extra cushion, so when I remove it, it's more likely to be to staying balanced, particularly if it's, if we have that between node that's going on. So if the current node then, the one after we do that rotate right, or if we didn't need to rotate right, if the node that we are is actually matching the key, well, at that point we can just return null. Because when I return null, then I can just go away. My node disappears. I've already rotated over to point to the new one, and we're done at that point. We can actually return that. So if I don't match it, if I'm not the node that needs to be worked on, then obviously I need to continue the algorithm. It's somewhere to my right at that point. So like we saw in the left case here, we're going to look at the right node and the right node's left node to see if they're black. That's the next left-leaning case of the situation. So if they're both black, then we're going to rotate right, like we just saw before. Again, if we're not the node that gets deleted, then it's coming from our right, and so we're going to make the space, to prepare for when that node does gets deleted. But by doing that rotate right, we might shift around what node we're talking about. So again, we're going to check if the new node situation after we moved everything around, if that matches, well then we're going to do basically the normal tree remove at that point. So at first we were able to determine like, hey, if I'm the node, I've already swapped out everybody else, I'm a leaf node at that point, delete me. Here we're saying I'm the node, but I have children underneath, and so I find the smallest child on the right by doing the find smallest method, just like we did in the binary search tree, and then I swap the values between me and the binary search, me and that child value, and then I delete the smallest one on the right, just like in the binary search tree. Though I will note that there is a more efficient balancing way to delete that other node, and so there is a separate function that you write to go and delete that. So if none of those situations happened, then I just make a recursively call. If I haven't returned already, if I'm not the node, I haven't returned there, then I just recursively call the child on the right. So there's a lot of little steps in that algorithm, but when you break it down, it really starts to make sense. The idea behind this is, as I move down the tree, I figure out, am I removing from the left or am I removing from the right? And then whichever way I'm going to be removing from, I kind of shift some nodes into that space, so that way when I delete it, it's going to still be a similar number of value. So I'm going to always keep it close to balance. So there might be situations where I don't move it. Might be a situation where I don't need to. And that's why I'm checking the red and black. I don't automatically move stuff left and right, but I do it when I have a red node or two red nodes or two black nodes, because I know, given those situations, whether I'm dealing with a binary search tree 1, 2, or I'm dealing with a 2, 3 node, and possibly needing to create some 3, 4 nodes so I have some space to delete stuff. So ironically enough, in adding, I'm trying to prevent getting those 3, 4 nodes. And deleting, I'm actually intentionally introducing those 3, 4 nodes. So when I delete something, I'm more likely to end up at a balanced state. All right, so wrapping up this conceptually, coding a remove function in the binary search tree is entirely optional for you. It is not in the book, but you can find that through the code downloads associated with the book. You're welcome to look at this code if you want to, but make sure you are writing the code yourself. It's not just an honor system, actually. It's actually going to be something that's going to be checkable inside of the submission tools. So you can automatically, when you submit it, see whether it was plagiarized or not. So there's no reason to do this. I am not factoring coding the remove method as something that you need to do to get an A in this class. Certainly not to get a B or a C. There's plenty of other points available, but if you really want to take on the challenge, there's a good chunk of points available for it, and if you're successful, you'll be able to get those points. So take this with that warning, and if you can get started, great. If you want to work on it and work on it together a little bit, great. If you want to skip it, at least now you've seen what it looks like, and you can make your best shot at attempting to delete nodes if you so desire.